Question: what's the likelihood of getting 5 hearts in a poker hand? Now you should know that a poker hand consists of 5 cards dealt out of a deck of 52. If we assume that the deck is well shuffled, then, so that each hand is equally likely, then the number of possible hands, well, we have to choose 5 cards out of the 52 in any order. It doesn't matter what order your hand appears in, you can rearrange it into any order you want. So there are this many possible poker hands. Out of those poker hands, how many of them have all hearts? Well, there are 13 hearts in the deck, so there's C of 13 5 ways to choose 5 hearts out of the 13. And that's the number of hands. That would give us a listing, if we listed all these, a listing of all the hands that have all hearts. The likelihood then of getting it, or the probability, and we'll talk about probability in the next chapter, we're kind of foreshadowing here. The probability is then the number of all heart hands divided by the number of all possible hands, or C of 13 5 divided by C of 52 5. I did that calculation roughly in my head on the idea that each one of these numbers is about 1/4 of each one of these. And I came up with about 0.0003. Actually, I think I used 1/5 because it kind of goes between 1/4 and 1/5. But it comes out around 0.0003, the probability of getting dealt 5 hearts. Pascal's triangle. If you've done the problems in combinations and calculated some of the combinations, the numbers here will seem familiar to you, especially some of these numbers down here in the middle. Let's first talk about how the triangle is constructed. We start with 1, and then below that we put a 1 and a 1. Now, below each 1 and to the left as we go down this side, below each 1 and to the right as we go down this side, we're just going to list 1s. Then, beneath any 2 numbers of a row, we're going to list the sum of those numbers. So 1 and 1 is 2, and that's going to go beneath the 1 and the 1, halfway between. Beneath the 1 and the 2, we'll have a 3. Beneath the 2 and the 1, we'll have a 3. Beneath the 1 and the 3, we'll have a 4. Beneath the 3's, we'll have a 6. Beneath 3 and 1, we have a 4. In each case, the number here is the sum of the numbers above it. The row grows by 1 number each time. That is, we add 1 place to the row. So the row gets bigger and we get this triangular configuration. Now, if we say that n is 0 in this row, 1 in this row, 2 in this row, 3 in this row, 4 in this row, and so forth, then what is the meaning of these numbers? Well, for example, the 6 here, okay, n is 4. Now we're going to let r be the number of the row listed diagonally. So r would be 0 for this row, 1 for this row, 2 for this row. So 6 occurs in the number 4 horizontal row and in the number 2 diagonal row. That is the combination C of 4, 2. Okay, C of 4, 2, of course, is 4 times 3 divided by 2 factorial, which is 6. And this is C of 4, 3. The pattern to the triangle is C of 0, 0 first, that's the 1. C of 1, 0, and C of 1, 1, the 2 1s here. Then the 3 numbers here are C of 2, 0, C of 2, 1, C of 2, 2. C of 2, 0, C of 2, 1, C of 2, 2, etc. That pattern goes on. One interpretation of these numbers is that C of 4, 2 says that there are 6 two-element subsets of a set having 4 elements. So there's an interpretation of combinations, and you can see it in Pascal's triangle. Okay? There's 6 possible two-element subsets of a set of 4. And you could list those. Because what do you do when you make up a two-element subset from a set of 4 elements? What you do is you pick 2 objects out of the 4. Order doesn't matter in a subset, so that it's a combination and not a permutation. If we have C of 4, 3, That's a number of 3-element subsets. Now you can list the number of 3-element subsets of a 4-element set, and there are 4 of them. But that's what this stands for. If we add across the row, this row could then be interpreted as the number of 0-element subsets, which is always 1 because it's the empty set. The number of 1-element subsets. The number of 1-element subsets is equal to the number of elements in the set. Remember, this is a 4th row. There are 4 elements in the set, because to get a 1-element subset, all you have to do is leave out an element of the set, and there are 4 elements that could be left out. And then there are 6 ways of getting 6 2-element subsets. There are 4 3-element subsets. I think I said that wrong. There are 4 1-element subsets because there are 4 elements in the set. 4 3-element subsets because there are 4 ways to leave 1 element out. And there's 1 4-element subset, which is the set itself. If we add all those up, we get 1 and 4 is 5, 11, 15, 16. That's the number of subsets of a 4-element set. Okay? 2 to the 4th power. Remember, it's 2 to the n for an n-element set. There are 2 to the n subsets in a set of n elements. Okay? So the sum of a row is the number of subsets of an n-element set, which is 2 to the n. Okay, when we add the numbers across any row, across row n, we get the number of subsets, and that number is always 2 to the n. So there's a lot of neat stuff about Pascal's triangle, and you'll see a lot more when you look at the problems. Let's look at one last counting example here. How many ways are there to rearrange the letters in the word Mississippi? How many different words can you get by rearranging the letters in the word Mississippi? Well, let's reason this out as follows. Let's suppose there are 11 letters here. Let's suppose we put those letters on tiles so that there are 11 tiles, each with one of the letters. How many ways are there to rearrange those tiles? Well, there are 11 factorial ways to put 11 tiles in different orders, because there are 11 choices for the first tile you put down, and then there'll be 10 left for the second, and 9 for the third, and so forth. However, not all of these ways of rearranging the tiles give us different spellings. That's because we have some repeated letters. If we see the 4 S's here, we don't know which tile each of those S's is on. I mean, it's on one of the S tiles, obviously, but there are actually 24 different orders that we could put the S tiles down in. Okay, so your 4 S's could appear in 4 factorial different orders. And they all look the same. Wherever the 4 S's are, in this spelling, for example, there are 4 different tiles that could be here, leaving 3 different tiles that could be this one, leaving 2 different tiles that could be this one, leaving 1 tile that could be this one. The 4 S tiles could then be put down in 4 factorial or 24 ways. Same thing applies to the 4 I's. And the 2 P's, you don't know which P is which when you look at it, unless you've numbered the tiles, or unless the tiles have some kind of markings on them. And we're assuming that the tiles are all identical. The tiles with a given letter on them are all identical. So that there are 4 factorial ways the 4 S's could appear, 4 factorial ways that the 4 I's could appear, 2 factorial ways that the 2 P's could appear. It follows that there are 11 factorial divided by 4 factorial times 4 factorial times 2 factorial different spellings. Because we have to divide the 11 factorial orderings first by the number of ways that we could have ordered the 4 S's, because there'll be groups of 24 spellings with the 4 S's in different orders. And then after we've done that, we still have to take account of the grouping of the I's, the fact that they could be grouped 24 ways, and then the fact that the P's could be grouped in 2 ways. So that we have to divide the 11 factorial orderings by the number of ways of ordering the S's, I's, and P's.